Welcome to This Explainer. Today, we're going to completely change how you look at a subject that, let's be honest, has caused a lot of us some serious frustration. If math problems tend to make your brain just shut down, you are absolutely in the right place. We're going to build a clear, working mental model of algebra right from the ground up. You know, why does algebra feel like some kind of secret code? For so many of us, it just feels like this chaotic jumble of arbitrary rules, kind of like a bunch of hidden tricks designed specifically to confuse you. But what if I told you it's not actually a pile of disconnected tricks at all? It's really a beautifully consistent system. So let's dive right into part one, the language of unknowns. We're going to see how visualizing relationships is absolutely crucial to stop memorizing and start understanding. Think about the real contrast here. Arithmetic? That's all about answering questions with numbers you already have in front of you. Like, totaling up your groceries at the store. But algebra steps in to handle those tricky moments when a number is missing or when it's changing. It gives us a language really, to ask, okay, what do I actually know and how are these things related to each other? Think of it kind of like the hidden pipes inside a massive apartment building. You can't actually see them behind the walls, right? But if someone turns a valve, the water pressure changes everywhere. Algebra works exactly the same way. It's a tool that helps you see what changes and what stays connected, even when some of the pieces are completely hidden from view.
Which brings us to section 2, what symbols really mean. Let's go ahead and demystify the absolute most intimidating part of the whole thing, the letters.
Look, at first glance, a symbol like X feels totally mysterious, maybe even a little scary. But symbols aren't magic secrets. They're literally just placeholders. They let us keep track of an unknown value without losing our overall logic. You can think of X as just a labeled box. You might not know what's inside that box quite yet, but having the label means you keep it in exactly the right place. Or think of it like a name tag at a big get-together. The tag doesn't tell you everything about the person's life. It just helps you keep track of who's who. Or even think of the frame of a door. The paint color might change, the door itself might change, but that frame, it holds the structure together so the door can actually function. Because really, symbols just compress all that messy thinking. A symbol like X doesn't have to be a fixed number. It can represent a number you just don't know yet, a number that might change, or even a general rule for a whole pattern of numbers. It's totally a game changer, because it allows us to describe these big, universal truths instead of just trying to solve one-off puzzles. All right, let's move on to section 3, expressions versus equations. We really need to distinguish between these two because they have very different jobs and they get mixed up all the time. So, an expression is really just a mathematical phrase. Think of something like x plus 4. It's not claiming anything is equal to anything else, it's just describing a quantity, like that label on a box we talked about earlier. But an equation makes a definitive claim that two things are exactly equal. It's a statement of balance, sort of like comparing two totally separate boxes and saying, yep, these weigh exactly the same. And that brings us right into section 4, the rule of balance. We're going to look at what is probably the single most misunderstood symbol in all of math. Okay, this idea right here, it's a massive mental shift. So many of us are taught to read the equal sign like it's the enter button on a calculator, right? Like it just means, hey, the answer comes next. But no, in algebra, the equal sign simply means perfect balance. It is telling you that the left side and the right side are just two different ways of describing the exact same amount. Imagine you've got two identical trays in front of you, and they're holding the exact same number of apples. If you take one apple off of just one tray, well, they aren't equal anymore, are they? The balance is totally broken. And that is exactly why any change you make to an equation absolutely must happen to both sides. No exceptions. Now that we've got the rules of balance down, let's check out section 5, unwrapping the unknown. This is where we get into the actual engine of how we isolate our missing pieces. You know, a lot of people think doing algebra means you have to somehow attack the letter X until it gives up and reveals itself. But that's completely backwards. We aren't just guessing random numbers, we're logically reversing the structure. Think about it like taking off a jacket that you put over a shirt. To see the shirt, you just have to take off the jacket. You're just doing the opposite move. And how do we do that? We use inverse operations, basically actions that reverse each other. Addition is undone by subtraction, division reverses multiplication. The exact operation that created the relationship is the exact tool you use to undo it and safely unpack that locked box.
And of course, to protect our perfectly balanced apple trays, we have to apply that move to both sides every single time. Now, sometimes x gets hidden inside a few different layers, and that's where brackets come in to protect the meaning. Let's think about this. Without brackets, 2x plus 4 simply means double your x and then add 4. But with brackets, like 2 then open bracket, x plus 4, it means you have to add 4 to x first and then double that whole result. The brackets are there to reveal the exact layers of the structure so you can see exactly what is attached to the unknown. Okay, let's bring all these fundamental shifts together in our final section, Part 6, Seeing the Hidden Structure. Let's see how all of this actually applies to real-world reasoning. Picture a standard wholesale delivery bill. Your total is going to be the cost per item times the number of items you got, plus some flat fixed delivery fee. Now, if you want to figure out exactly how many items were in that box, what do? You reverse the structure. You take the total, subtract that fixed fee first, and then divide what's left by the cost per item. Boom. You just traced the logic backwards to turn a confusing total into a totally readable system. If we break this down, you'll notice how totally different looking equations are actually asking you for the exact same structured reasoning. Whether x is combined with 5, whether it's scaled up by 3, or sitting deep inside some brackets, the hidden story is identical. You're not actually memorizing 100 different tricks. You're applying one incredibly powerful idea. You just reverse the steps while keeping everything perfectly in balance. So there it is. You've got a completely new lens now. You know that an unknown isn't just chaos on a page. It's simply a quantity sitting safely inside a structure. So I'm going to leave you with this. The very next time you come across a problem with unknown, are you going to freeze up, or are you going to look closely and trace the structure? Thanks so much for joining me on this explainer, and I'll catch you next time.